Right, good morning. So, speaking of course, you know that there's a quiz today, right? It's 5:40. So, there's a note about that. So, today we're going to continue our example that we started last time. So, essentially, we're discussing what kind of situations can be formulated using binary variables. And last time we actually sort of looked at the following problem. So, suppose that you have a bunch of different products, and then you either produce nothing, or if you produce something, then you produce it in a certain amount. So, you can think of this as a sort of, there's a certain setup. So, in order to justify the setup cost, you actually need to produce at least a certain amount of quantity. And last time we formulated it using binary variables, so which basically means that such situations can be modeled using binary variables. So today we're going to look at two more situations. So this is same example part B. So suppose that you choose projects from among, let's say, 10 projects to invest. So each project has a certain profit. And each project has a certain capital requirement. So, you can think of this as just like the example that we looked at. Basically, we had like 10 projects, and then each one has a certain profit associated with it, and each one has a certain capital requirements. So you have a certain budget constraint, and so on and so forth. Let's say if projects 1 and 2 are chosen simultaneously, then there is an additional profit of let's say P Turkish liras, whatever P is, okay? So what does this mean? So suppose that project 1 has a certain profit, project 2 has a certain, probably different profit. So if I pick project 1 and 2, I already sort of earned those profits, the profits from 1 and 2. But if I pick them simultaneously, if I pick them at the same time, then there's an additional profit as well. Okay, so basically, I'm going to get P1 plus P2 plus P if I pick 1 and 2 at the same time, where P1 is the profit of project 1 and P2 is the profit of project 2. So the question is, how can we model such a situation? So basically, suppose that I'm getting individual profits from each project. Okay, so this was the example we looked at. But there's this extra requirement that if I happen to choose 1 and 2 at the same time, then there's an additional profit. Okay? So there's an extra profit of P Turkish liras. And the question is, how can we model this situation? So again, I'm not giving you the whole problem. So suppose that this is one of the requirements of the problem. So essentially the question is the following. How can we formulate this as constraints? Okay? First of all, is the requirement clear? So essentially what this says is the following. Again, you're choosing projects, okay? There's a set of projects from which you choose, or you make choices. Each project has a certain profit. So let's say project 1 is a profit of P1, and project 2 is a profit of P2. So if you pick those projects, then you obtain those profits. But in addition, there's this extra requirement that if you pick 1 and 2 at the same time, then there's an additional profit of P units. So basically, if you pick 1, you get profit 1, P1. If you pick project 2, you get P2 as a profit. And if you pick both of them, then you get an additional P as an extra sort of profit in some sense. So if you pick projects 1 and 2, then you get P1 plus P2 plus P as your total profit. Is that clear? Is the question clear? Okay, so now the question basically is the following. How can we formulate this using IP constraints? How can we formulate such a situation? Well, if you think about this a little bit, essentially, I need to figure out in which case do I get this additional profit, right? So I get this additional profit if and only if I pick 1 and 2 at the same time, right? So as a result, what I'm going to do is the following. I'll define a binary variable, which I'm going to call z, and set this equal to 1 if projects 1 and 2 are chosen simultaneously. And I'm going to set it equal to 0 otherwise. So think of z as an indicator variable that tells me whether I'm picking 1 and 2 at the same time or not. Okay? If I pick 1 and 2 at the same time, then obviously z will be equal to 1. And if I don't pick at least one of them, then z will be equal to 0. Okay? So in other words, z is equal to 1 if and only if I pick 1 and 2 at the same time. So simultaneously basically means at the same time, right? All right, so I still need the usual binary variables, xj. So it's going to be 1 if project j is chosen. And it's going to be 0 otherwise. And I'm going to define this for each of the 10 projects. Now, if you think about this a little bit, there's a certain relationship between z and xj's, right? Certain xj's at least. So, the value of z actually depends on x1 and x2, basically, right? Why is that? Because z will be equal to 1 if and only if, project 1 is equal to 1 and project 2 is equal to, or x1 is equal to 1 and x2 is equal to 1, right? So essentially, I have the following relationship. So z will be equal to 1 if and only if x1 is equal to 1 and x2 is equal to 1. Does everybody see that? That's pretty straightforward, right? So basically, if this is true, then I'm picking 1 and 2. In that case, z has to be equal to 1. And conversely, if z is equal to 1, then I have to pick both 1 and 2 as my projects, right? Okay? So the question is the following. How can I relate z, x1 and x2? So how can I write constraints to make sure that, this is always satisfied, basically? So let me repeat the question again. How can I write IP constraints to make sure that this relationship is always satisfied? Okay? Now let me start with one possible solution. So for example, I can set z equals x1 times x2, right? Now if you think about this a little bit, this relationship actually satisfies this relationship, right? This equation actually satisfies this. Right? So z can be 1 if and only if both of them are equal to 1. And if at least one of them is equal to 0, then z will be equal to 0. Right? But what's the problem with this formulation? So we multiply two variables. So basically, actually, this is a correct solution, but this is nonlinear. So this doesn't work for us. It's nonlinear because we're actually multiplying two variables. Okay? In an IP constraint or LP constraint, we can never multiply two variables. Okay? So this is something you have to be extremely careful about. So despite the fact that this is a solution, this is not the solution I want. Okay? So now the question is the following. How can I reformulate it as an IP or LP constraint? So
Can't say anything to satisfy this. For example, z equals x1 plus x2 minus 1.
So let's think about it. So z equals x1 plus x2 minus 1. Does it work? Well, for example, if x1 is equal to 1 and x2 is equal to 1, then z is indeed equal to 1. So that's good. But if x1 is equal to 0 and x2 is equal to 0, then z is equal to minus 1, right? So that's not something I want. Okay? So as a result, that doesn't quite work either.
x1 plus x2 greater than equals 2 multiplied z.
So x1 plus x2 is greater than or equal to 2 times z. So again, in this case, this can be 1, this can be 1, and this can be 0, right? Okay? Actually, we're getting close to the solution, so which is good. So let me actually change it this way. So let me make it z is not equal to, but z is actually, let's say, greater than or equal to. Now, if x1 is equal to 1 and x2 is equal to 1, then this difference is equal to 1, right? Then this forces z to be equal to 1. So that's good. Okay? If at least one of them is equal to 0, okay, let's say this is equal to 1 and this is equal to 0, then the right-hand side becomes 0. So I want z exactly to be equal to 0 in that case, right? So this doesn't satisfy that yet. Okay? So I should add something else then. Okay? So what if I add these two constraints as well? So I claim that actually these constraints actually work. Okay? So let's just verify that it's true. So let me look at the case first when x1 and x2 are both equal to 1. If both of them are equal to 1, then the right-hand side becomes 1, right? So if the right-hand side is 1, then z is greater than or equal to 1, which means that z has to be equal to 1, because z is a binary variable. Okay? And then if z is equal to 1, these are also satisfied, basically, right? Everything here is satisfied. So on the other hand, let's say if x1 is equal to 0, well, if x1 is equal to 0, then this constraint forces z to be 0, right? So, this constraint becomes an unnecessary constraint because z is equal to 0, this one is satisfied. And if I look at this constraint, so the right-hand side cannot be more than 0 in that case, right? Because at least one of them is equal to 0. So z is always non-negative, so this is also satisfied. So as a result, these constraints indeed make sure that this relationship is satisfied. Okay? So once again, if you like, you can just sort of, write a table. So look at the different values of x1, x2. So if x1 is equal to 1 and x2 is equal to 1, it's not too hard to see that z has to be equal to 1. Okay? If x1 is 1 and x2 is 0, you can verify that z is 0. So in this case, z is also 0. And finally, in this case, z will also be equal to 0. Okay?
If they are both 0, z can be minus 1.
If they're both 0, then z is less than or equal to 0, z is less than or equal to 0, right? And this says z is greater than or equal to minus 1. Okay? But z is always greater than or equal to minus 1. This is not equal to, this is greater than or equal to, right? Z cannot be minus 1 because z is a binary variable. Okay? So that's why I cannot use equality constraints, but I have to use inequality constraints. Okay? Is this clear? So, any questions about this? So, what's the sort of main message here? Well, the message basically is the following. So, if you end up with a situation where you have to multiply two binary variables, okay, you can always turn them into LP constraints or IP constraints, basically, okay? So, this relationship can always be written in this form, okay? And this is really nice because, as I said, you take a nonlinear constraint and you write this linear constraint, so which is really nice. Of course, the price you pay is that here's a single relationship, so you have to write three constraints, okay, to make sure that it's satisfied. So as a result, you can take this nonlinear constraint, you can write these linear constraints, but you have to write, more than one linear constraint, basically, okay? So that's the trade-off. But for our purposes, this is going to work because this is what we want, okay? So we want to make sure that we have IP or LP constraints. So as a result, these three constraints ensure that this relationship is always satisfied. Any questions about that? Yes?
Geçen derste P ile Q'lu yapmıştık ya, hani P'nin tersi O Q'ya dönüştürmüştük böyle bir şey. Onu yine burada da uygulayabilir.
Yes, you can, but you have to be careful. So there are two different requirements. If z is equal to 1, then this has to be satisfied. If this is true, then that has to be satisfied. So you have to do it in two stages, basically, okay? And you have to sort of define new variables, new constraints, and so on and so forth. But this does it directly. So this works directly, okay? Other questions? So, does everyone understand this example? So I just want to make sure that this is understood. Okay? So as a result, the second message is that so you can use binary variables to formulate a situation where you have to multiply two binary variables. Okay? So that can still be formulated as linear constraints, which is good. Okay? For example, how would I modify my objective function? Well, to the previous objective function, I just need to add p times z, basically, right, to my objective function. So if z is equal to 1, then I'm going to get additional p. And if z is equal to 0, then I'm not going to get that additional profit, right? Once again, any questions about this? Other questions? All right. So there's one more situation that I want to discuss. That's part C. So this is known as piecewise linear functions. Now, in some cases, in some applications, the cost is not quite linear, but it's actually it has a piecewise linear form. What does that mean? So, for instance, suppose that you're actually managing a factory, okay, and you buy raw materials, let's say, okay. So, what they can do is the following: they can tell you that if you buy up to 100 units, let's say, then I'm going to charge you one lira per unit. But if you buy more than 100, then I'm going to charge you only 0.75 or something like that, right? So now that's not a linear actually function, but that's actually a piecewise linear function. Okay, so if you buy less than or equal to 100, there's a certain slope, and if you buy more than 100, then there's a certain other slope, right? The slope of the function changes. Okay, so that kind of situations arises in different settings. So suppose that we have the following function. So think of this as a cost function. So this is going to be equal to 2 times x if x is between 0 and 100. It will be 100 plus x if x happens to be between 100 and 200. And finally, it's going to be 2x minus 100 if x is greater than 200 but less than or equal to 300. So think of this function in the following way. So x is the number of units of raw material I buy from a certain supplier, let's say. And this is the price that supplier charges, for example. Okay, so depending on the value of x, I'm going to use a different function. So as a result, this is my cost function, basically. Okay, and what I'm going to do is I'm going to just draw the graph of this function. So this is basically what the function looks like. So here's my x. This is my function c of x. So when x is between 0 and 100, this is just 2 times x, so which looks like this function right here. If x is between 100 and 200, we have 100 plus x, so the slope now changes. So this is the value of function here. And then if x is between 200 and 300, I have 2x minus 100. So again, I have the same slope as the first part, so this is what my function looks like. So the value here is equal to 200. What's the value here? So it's going to be 300, basically, if you just plug in 200. So you have 300. And what's the value of my function here? So it's going to be 2 times 300 minus 100. It's going to be 500, right? Okay, so this would be a typical example of a piecewise linear function. So this is called a piecewise linear function because, for example, in this case, there are 3 pieces. The first piece, second piece, and third piece, and each piece is a linear function. Okay, so that's why it's called a piecewise linear function. The function overall is not a linear function, by the way, because linear functions actually have to have a certain slope, and it has to continue, right? Okay. However, in this case, my slope changes depending on which piece I'm looking at. So as a result, this is not a linear function, but it's a piecewise linear function. So each piece is a linear function in some sense. Okay. So now the question is, how can we, for example, formulate this cost function? Okay, so again, this is not something that we have seen earlier, but it turns out that we can also model this type of situations. I mean, of course, I cannot use c of x directly because c of x is not a linear function. Okay, I have to do something about that. Alternatively, you can also sort of think of c of x as a profit function as well, okay, depending on the application. So for now, for this example, let's just assume that c of x is a profit function. Doesn't really matter, but so essentially the profit depends on my production levels, and for different levels of production, I have different levels of profit, let's say, okay? So what I want to do is I want to maximize my profit. And suppose that there are some additional constraints that I need to satisfy, which I haven't specified, but suppose that this is part of my problem, and my goal is to maximize my profit. Okay? So the question basically is the following. How can we formulate this situation using IP constraints, basically?
Çözümle alakalı değil aslında ama böyle bir şeyimiz, grafiğimiz olduğu zaman kimse 200 ve 300 arasında almak istemeyecektir değil mi? Çünkü yani amount of x arttığı zaman fiyatta düşsün ki hani daha çok almak istesin. Ama
So think of this as my total profit function. Okay, so what does that mean? So for example, in this interval, my profit is given by 2 times x. Okay, in this interval, maybe I need to sort of hire some additional workers. So as a result, my profit goes down. Okay, and then here, maybe I already have some workers, and my profit goes up again, or something like that. Okay, so think of this as my profit function. So if I produce anything here, this is going to be my profit. If I produce anything here, this is going to be my profit. And if I produce anything here, then this will be my profit, basically. Okay? Yes?
Again, binary varieties.
Okay.
If we choose to produce in the region 1
Uh-huh.
or region 2 or region
Okay, that sounds good. So let's try and see if that works. So let me call this region 1, region 2, and region 3. Okay? So what I'm going to do is the following. I'll define a binary variable, which I'm going to call zi. So it's going to be equal to 1 if the production is in the first region. Production level is in region I. And it's going to be 0 otherwise. And since I have 3 regions, I'm going to have 3 binary variables, okay? So this looks like a good start, basically. All right, what else do I need? I need to know how much I produce, so let me call it x. X is the, so think of this as the level of production. Level of production basically means, you know, how much I produce, okay? What else? Now, there's one thing you have to be careful about here. So, as I said, depending on different regions, your profit function changes, right? So, as a result, depending on which region you are, the unit profit also changes, right? Profit per unit also is different. So, for example, in this region, the profit per unit is 2 actually, right? Okay. Whereas if you're in this region, then if you look at the incremental, if you look at the slope of this function, then the profit only goes down to 1, right? For each additional unit I produce, I get only 1 profit basically, right? Okay. And if I'm in this region, then the profit becomes 2 again. Okay. I'm talking about unit per unit profit. Does everybody say that? So in other words, the slope of this function in each region tells you the unit profit basically, right? Does everybody see that? Everyone knows slope, right? So slope is the tangent of the function or something like that, right? So basically, the slope determines the per unit profit. Okay? So in this region, each unit actually brings you a profit of 2. Okay? In this region, each unit brings you only a profit of 1 actually, because this is incremental. Okay? In this region, each profit brings you, again, a profit of 2. Okay? So as a result, when I compute the profits, my per unit profit changes depending on which region I am. Okay? So to take into account that effect, I'm going to define the following way. Define the following variables. I will simply define xi to be the level of production in region I. And I will be 1, 2, or 3. So what does that mean? So essentially, here's what I'm thinking. So suppose that x is equal to 150. Okay? If x is equal to 150, then I should first produce 100 in this region, right? And then I should produce 50 more in the second region. Okay? If x is equal to 220, then I'm going to produce 100 in the first region, plus 100 in the second region, plus 20 in the third region. Okay? And it's not too hard to see that if I add up x1 plus x2 plus x3, what do I get? I get x exactly. Okay? So as a result, let's start writing down those relations. So x is equal to x1 plus x2 plus x3. So x1 denotes how much production I have in this first region. What's the largest value of x1? So x1 cannot be more than 100. So let's write it down. What about x2? Well, the same is true for x2, and the same is true for x3 as well. All right. Now, there should also be a relationship between ZIs and Excise, right? Why is that? Because, for example, if Z1 is equal to, let's say, or if Z2 is equal to 0, okay, then my X cannot be in this region, basically, right? Okay? Well, if Z2 is equal to 0, then X cannot be in this interval. So X then will either be in this interval or in this interval, basically, right? So as a result, there's a certain relationship between Xis and Zis, and I have to express those relations. Okay? In addition, there's the following requirement. So for example, x2 can increase only if x1 actually comes up to its upper bound, basically, right? So in other words, if x1 is not equal to 100, then x2 cannot be positive. Okay? So the only way I can start increasing x2 is when x1 actually hits its upper bound. Does everyone see that? So essentially what I'm saying is the following. If my production level is here, then first I have to use x1 up to 100. And only after that, x2 starts increasing, basically, right? So in other words, there's a certain relationship between the values of x1, x2, and x3 as well. So I cannot have a situation where x1 is 0, but x2 is equal to 2, for instance. Right? So first I have to start using x1. Then I have to start increasing x2. And finally, I have to start increasing x3. Okay? So there's a certain order in which I have to do things. And my question is, how can I write them as constraints? Well, first of all, let me start with the easy case. So is there any relationship between Z1, Z2, and Z3? And what is that?
Z2 cannot be 1 if and only Z1 is 1.
Okay. That's true. I was going to start with an easy relationship. So since this determines whether I'm going to be in the first region or second region or third region, and since I can be exactly in one region, okay, so what kind of a constraint does it imply? Exactly. So Z1 plus Z2 plus Z3 has to be equal to 1. Okay? So which means that I have to exactly in one region. Okay? Okay, what else do we have?
Zi is bigger than or equal to Zi minus 1.
Zi is bigger or equal to Zi minus 1. Why is that true?
Kendisinin bir olması için diyelim. Mesela Z1 bir olmadan x için mi? Pardon.
So let's try to think of in the following way, okay? Think of this problem in the following way. So what does it mean for Z1 to be 0? So if Z1 is equal to 0, then my X will not be in this interval, right? That's what it means, okay? So which means that my X then will either be in this interval or in this interval, okay? All right, so if Z1 is equal to 0, then what does that imply about X1? Exactly. If Z1 is equal to 0, then X1 has to be equal to 100, right? Because that means that I'm not going to be in the first region, so I have to move over to the second or the third regions. But to do that, the first thing I need to do is first increase X1 up to 100. Does everyone see that? It's simple logic, right? Okay. So now my question is, that means that there's a certain relationship between X1 and Z1, basically, right? So the question is, what is that relationship? So if z1 is equal to 0, then I want this to be true. Okay? And how can I enforce this? So what does this do? Well, if z1 is 0, then this says that x1 has to be at least 100. Okay? This one says that x1 cannot be more than 100. And if I combine the two, then x1 has to be equal to 100, right? Does everyone see that? Okay. All right, so what else do we have? Anything else? So now let's think of the following way. If my production is in this region, right? If my x is in this region, then both x1 has to be equal to 100 and x2 has to be equal to 100 as well. Okay? So how can I force that? So that means that there's a certain relationship between x2 and z3 as well. Okay? So what's that relationship? Does this work? Well, if z3 is 1, I'm forcing x2 to be equal to 100, basically, right? Okay, and if z3 is 0, then x2 is non-negative, basically. Okay? So basically this tells you that if z3 is equal to 1, then I have to make sure that x2 is also at least 100. Okay? Similarly, if z3 is equal to 1, okay, then that means that these two have to be 0, right? That also forces x1 to be equal to 100 as well. Why is that? Because z1 is 0, so this forces x1 and x2 to be equal to 100. Okay? Anything else? So do we need anything else?
X3 greater than equal 100 multiply Z1 and Z2 plus.
So x3 is greater than or equal to 100 times?
Multiply Z1 plus Z2.
Z1 plus Z2. Well, there's a problem with this one, right? So this one says that if z1 is equal to 1, but z2 is equal to 0, then this is not true actually, right? Okay? So as a result, this doesn't quite work. Okay, do we need anything else? So there's one more thing you need to be careful about. So if z1 or z2 is equal to 1, okay, so which means that my production level is either in the first region or in the second region, then x3 should be equal to 0, basically, right? Okay? So in other words, if my production level turns out to be either in this region or in this region, then x3 has to be equal to 0. So it cannot be in this region. So the question is, how can I write it as a constraint? So now I'm going to have an upper bound on x3, right? So the usual upper bound is 100. But I want this upper bound to be 0 if z1 or z2 is equal to 1. Okay? Exactly. So if I write it this way, so this ensures that if z1 is equal to 1, okay, then z2 has to be 0 because of this constraint. Then the right-hand side becomes 0. Okay? So this makes sure that x3 cannot be positive. Okay? By the same reasoning, if z2 is equal to 1, then by this constraint, z1 has to be 0. So the right-hand side becomes 0. This forces x3 to be equal to 0 as well. Okay? Finally, by the same reasoning, I have to make sure that if z1 is equal to 1, then x2 has to be 0 as well. Okay? If my production level is in the first region, then z2 has to be equal to 0. Okay? How can I write as a constraint? So what does this do? Well, if z1 is equal to 1, then that means that I'm in the first region. Okay? So then that means that x2 has to be 0, basically. Okay? So let's just quickly go over each case one by one. So suppose that z1 is equal to 1. Okay? Let me look at my constraints. Now, if z1 is equal to 1, so these are, let's say z1 is equal to 1. So let me look at my constraints. So if z1 is equal to 1, this says that x1 is greater than or equal to 0. Okay? This says that x2 is greater than or equal to 0 because z3 has to be 0, right? Because of this constraint. So z1 is equal to 1 means that z2 is equal to 0 and z3 is equal to 0, right? Okay? So this means that x2 has to be non-negative. Okay? And if I look at this constraint, then z1 is equal to 1. And this right-hand side becomes 0. So that means x3 has to be less than or equal to 0. And if I look at this constraint finally, x2 has to be less than or equal to 1 minus z1. So since z1 is equal to 1, this becomes 0. So x2 is less than or equal to 0. So I also have, of course, non-negativity constraints. So xi has to be greater than or equal to 0. I from 1 to 3. Now if I look at these constraints, well, x2 less than or equal to 0 and greater than or equal to 0, make sure that x2 is 0. And x3 less than or equal to 0 and greater than or equal to 0, make sure that x3 is 0. So this implies that x2 is equal to 0 and x3 is equal to 0. Does everyone see that? So if these are the values of my variables, then my constraints make sure that x2 and x3 have to be equal to 0. Okay? So let me look at the second case. So suppose that z1 is equal to 0, z2 is equal to 1, and z3 is equal to 0. So let me look at my constraints again. If I look at the first one, so this says that x1 should be 1 minus c1, 100 times 1 minus c1, but z1 is 0, so this forces x1 to be equal to 100. Okay? What about this one? Well, if z3 is equal to 0, then x2 is non-negative. What about this one right here? So I'm looking at z1 and z2. So z1 and z2, one of them is 0, the other one is 1. So the right-hand side still becomes 0. Right? So 1 minus 0 minus 1 is equal to 0. Right? Okay? So this forces x2 to be less than or equal to 0. Finally, if I look at this one, so since z1 is less than or equal to 0, then x2 should be less than or equal to 100. And that's exactly what I want, right? So x1 will be equal to 100. x3 will be equal to 0. x2 can be anything between 0 and 100, basically. Okay? And finally, let's look at the last case. So let's say z1 is 0, z2 is 0, and z3 is equal to 1. Then let me start with the first one. Since z1 is 0, this forces x1 to be equal to 100. since z3 is 1, this forces x2 to be 100 as well. Okay. What is the value of x3? Well, z1 and z2 are both zeros. Now the right-hand side becomes 1. So I have x3 is less than or equal to 100. What about this one here? So since z1 is 0, x2 should be less than or equal to 100. So if I look at this constraint and this constraint, they force x2 to be equal to 100. If I look at this constraint and this one, they force x1 to be 100. And so as a result, in this case, x1 and x2 should both be equal to 100, and x3 can be anything between 0 and 100. Okay? So as a result, basically, it seems like these constraints take care of all possibilities. Okay? So of course, again, the price you have to pay is that you have to write down a lot of constraints. Okay? So, but essentially, the constraints are not too hard to understand, hopefully, right? They just make sure that there's a certain relationship between x1, x2, and x3. Okay? And essentially what you're doing is the following. So you cannot increase x2 before x1 actually hits its upper bound. Okay? You cannot increase x3 before x1, so x1 and x2 both actually hit their upper bounds, and so on and so forth. Okay? So essentially the constraints only make sure that these are true. Okay? So the constraints make sure that you can have a situation where x1 is equal to 1, x2 is equal to 5, and x3 is equal to 7, or something like that. Okay? So there's a certain relationship in the order of increasing x1, x2, and x3. Okay? So you start increasing x1, and when x1 is equal to 100, only then you start increasing x2. And when x2 is equal to 100, only then you start increasing x3. Okay? So as a result, these constraints make sure that you have the right formulation. So now my question is the following. Of course, we need to make sure that zi's are binary variables for all y. So my next question is the following. How can I formulate the objective function? So how can I express my total profit? Well, once again, I mean, the easiest way to think about this is the following. So, the variables x1, x2, and x3 help us, basically, in terms of computing our total profit. So, as I mentioned at the beginning of this example, the per unit profits are different, right, in different regions. Okay? So, one way to think about this is each additional unit here actually brings you a value of 2. Each additional unit here actually brings only a value of 1, which is slope of this part. Okay? And each additional value here, each additional item here actually brings you a profit of 2 again. Okay? So my question is the following. How can I express my total profit in terms of my variables? Well, but zi's are binary variables, right? So I have to write it in terms of x1, x2, and x3 somehow. Okay? So what's the objective function? Well, when we think about this is the following. So try to think of the profit as the profit from part 1 plus profit from part 2 plus profit from part 3. Okay? That's going to be the easiest way to sort of understand this. So what's the contribution of the first part? So it's going to be 2 times what? 2 times x1, exactly. So 2 times x1 will be the profit contribution of the first part. Okay? Now, what is the contribution of each unit in the second region? Only 1. Okay? How many units do I produce in the second region? x2. So as a result, I'm going to have 1 times x2, or just x2, plus I have the third region, and each unit actually brings me a profit of 2, so I'm going to have 2 times x3. And that's exactly my objective function, right? Okay? So essentially, defining your variables xi help you both in terms of modeling your constraints and your objective function as well. Okay? So despite the fact that this is a piecewise linear function, we were able to express it as a linear function. But note that now these are my variables are x1, x2, and x3 rather than x itself. Okay? So in terms of x, this is not a linear function. But I turned it into a linear function in terms of x1, x2, and x3. Okay? Yes?
We are trying to maximize our profit, so if we write as our objective function x1 plus x2 plus x3, what would change? Instead of 2x1 plus x2 plus 2x3.
Then you would just maximize your production. You wouldn't maximize your profit. Okay? x1 plus x2 plus x3 is my production level. Okay? So what I'm interested in maximizing my profit. Okay? And the problem here is the following. So as I said, the contribution to profit of each part is different from one another. Okay? So as a result, we have the contribution from the first part plus the contribution from the second part plus the third part. Okay? And the constraints make sure that x1, x2, and x3 take the values they're supposed to take, basically. Okay? Other questions? So once again, the bottom line is the following. So if you ever come across such a function, okay, you can still formulate it as an integer programming problem, and you can use binary variables. I mean, the constraints look a bit complicated, but if you think about it at a high level, the idea is pretty simple, actually. Okay, so you just make sure that your variables can increase only in a certain order, basically. Okay, so you know, as I said earlier, for example, x2 cannot be positive before x1 becomes 100. Okay, and essentially you have to write constraints to make sure that those are satisfied. Okay, so you can never have a situation where x1 is equal to 50, x2 is equal to 20, and x3 is equal to 10, for instance. Okay, that's not a solution because x2 cannot increase before x1 is equal to 100, basically. Okay. Similarly, x3 cannot increase before x2 is equal to 100, and the constraints actually make sure that they are the case. Okay. So the constraints make sure that there's a certain relationship between Excise and Zi values, Zi variables. Okay. And if you think about this, all these constraints are linear constraints, basically, right? Does everybody see that these are linear constraints? So all of these constraints can be written in the form a constant times a variable plus a constant times a variable and so on and so forth is less than or equal to something else, right? Okay. Any questions? All right, so good luck with the quiz tonight.